Good day, everyone, and once again we are back together, and we are going to be looking at another example of Euclidean geometry. And this time, of course, we're going to be applying more of the proportionality theorems. So if you haven't subscribed, please just make sure you're part of the family. All right, and this is from the May 2023 exam. Right, very interesting question this. Okay, let's get right into it. So they say to us we've got a diagram which is, or rather in the diagram, we've got TR, which is a diameter. Now, ladies and gents, I want you to always remember, the moment they give you a diameter, okay, please go and look for, the angle at semicircle. So I can already see that K1 plus K2 should be able, in fact, let me just indicate it more nicer. In this case, so K1 and K2 should give you 90 degrees, right? And that's an angle at semicircle. But also note that you'll also have P1 and P2, right? That should also be the angle at semicircle there, right? So in this case, we know that we've got those, right? So they say to us KR, or rather called TP and KR are produced to intersect at S, right? So they simply mean that's a straight line. So the moment they say that, look at angles, sum of angles on a straight line, okay, or you can even look at, actually sum of angles on a straight line, or sometimes vertically opposite angles, right? So they say chord PK is drawn such that PK is equal to TK. All right, so probably we're going to use that later on, right? But what I do note there, okay, so, and this I like doing for the sake of, just being able to work through the diagram. So if you go down and look at the questions, they want us to prove several things. But what I'm going to do is let's first work within the diagram and see who's who in this zoo, right? Okay, so first of all, I would notice in this case that P3 should also be equal to 90 degrees, right? So this angle here, which is P3, should give us 90, right? And you can either say exterior angle of a cyclic quad. Let me just highlight that cyclic quad that we have there. Right, so remember, this guy would be a cyclic quad, right? Let me just try to make this as clear as possible, right? So you've got that cyclic quad, which is PTKR, right? So that means we've got the exterior angle of a cyclic quad, okay? Now, they've given us also this angle here that they said is actually equal to actually no, not they haven't given us the angle per se, but we know that P1 in this case, now because we've got these two being equal, TK as well as PK, right? So that makes triangle PKT an isosceles triangle. So for that reason, ladies and gents, I'm going to make this angle here, right? Let's call it angle X. All right, and then check which other angle would be equal to X or related to X in that case, right? Now, that means that this angle T1 and T2 should also be equal to X as well, okay? Right, I want to just draw it such that I can show it's the entire angle. So that angle would be X, right? Because you've got an isosceles triangle, the base angles of an isosceles triangle, PKT, in this case, are equal, right? And so what that also means is that R3 would be equal to X, okay? These are angles at same segment, so P1 and P3 should be equal, right? But please also note in this case, it means that you've got R1 also equal to X, right? That's the exterior angle of a cyclic quad again. So this guy here is equal to x, okay? And then what that simply means is that therefore angle, let's see, let's just write it in a different color. So that means that angle, yeah, let's use that green there. So this angle here should be 90 minus x, right? Sum of angles on a straight line, this P3 is 90, R1 is x, and so it means that angle S would be equal to 90 minus x. But, ladies and gents, what it also means, okay, so if you look at in this triangle PTK, no, not PTK, rather, RKT, yeah, RTK rather. Okay, so this entire triangle here, right? This guy is x, and that's 90. So that means that this angle here, now note, this angle here should also be 90 minus x. Sum of angles on a straight line, right? Okay, so this angle here, so T2 is equal to P2, okay, which is 90 minus x as well. There's angle at same segment. Right, the unfortunate thing about Euclidean geometry is that you have to work inside the that drawing as much as you possibly can, right, to get to the answer, right? So what else do we know there? All right, so what I'm going to try and do is let's look at the questions and see if we can answer, right? So they say prove giving reasons that SR is a diameter of a circle passing through SP and R, right? So, okay, so they're saying if suppose we had a circle here that passed through these points, right? Yeah, it's not really the nicest drawing of a circle, right? But in this case, with obviously S trying touching that circumference there, right? So to prove that it's a diameter, that SR is a diameter, all we need to prove is that P3 is equal to 90. We've already done that, ladies and gents. Okay, so to do so, what how we got there is that first we found angle K1 and K2, right? And we said in this case we know that, okay, so I'm just going to change the color there. Okay, so we knew that K1 plus K2, okay, so I'm going to say K1 plus 2, right, is equal to 90 degrees. And why is that? This is angle at semicircle, right? Circle. Okay, so I'm just going to draw that circle there. So K1 plus K2 are equal to 90 degrees. These are angle at semicircle, right? And in this case, so that meant that P3 is equal to K1 plus K2. So P3 is equal to K1 plus K2. Okay. So which means P3 is also equal to 90 degrees. But what was the reason there? That's the exterior angle of a cyclic quad. Okay. All right, cyclic quad. All right. Okay, I'm not going to complete that. Right, so we know that now P3 is equal to 90 degrees. So therefore, it means that SR would actually be equal to a diameter. So SR is a diameter. Why would that be the case, right? Because in this case, P3 would be the angle at semicircle, right? So in this case, that's the converse of angle at semicircle. Okay, semicircle. Right. So we know that angle at, if SR is the diameter, then definitely P3 would be the angle at semicircle. Right. I hope that makes sense, ladies and gents. right? Let's go on to the next one. Now they say prove that angle S is equal to P2. Let's see if we've already done so. Angle S, okay, so this is the 90 minus X angle, right? Angle P2, okay, so it's that one in there, and we've already, okay, I'm gonna remove the circle here. So we've already actually proven, in a sense, that angle P2 is equal to that angle S. So what we did was to just name our angle S, P1 as X, right? So let's do so, right? Let's prove that P2 is actually equal to angle X, right? 90 minus X rather. Right, so how did we do so, right? So the first thing that we did was to name this angle X here, right? And what that meant was that this angle T1 plus T2, in fact, let's start there, right? So if we said T1, okay, let's just use a different color again. So we said T1 plus T2, okay, right, should be equal to angle R1, okay? Right, so we named it X. Let's say this is equal to X. Now, why are they equal? Because this is the exterior angle of a cyclic quad, right? The exterior angle of a cyclic quad. Okay, right. So, because those two are equal, right? So we named it X, right? Now we already know that P3 is equal to 90. R1, right, is X. So therefore it means that angle S, okay? So let's say angle S would be equal to 90 minus X, right? Why is that? Those are some, that's angles of a triangle, right? Sum of angles on a triangle. So you can try that out. So it means that P3 plus R1, okay, angle P3 plus R1 plus angle S would be equal to 180, right? And in this case, it means to get angle S, you are simply going to say 180 minus P3, which is 90, minus R1, which is X, okay? And that's how we got to that 90 minus X. So we've got the value of angle S in this case being 90 minus X, right? All right, so that's 90 minus X, right? So we've got the size of angle S, right? Now, in this case, so now if we take angle T2, if you remember, right, we know T1 plus T2 in this case would be equal, no, not T1 plus T2 rather. So now we go in triangle. So in triangle, P, what's that? So that's RKT, right? In triangle RKT, KT, so meaning inside this triangle here, right? We found in this case, so that means that angle P1, okay, so let's say angle, so we've already said T1 plus T2, okay, so that angle would be equal to P1, right, which is equal to X. But why is that? Right, the reason is that these are base angles of an isosceles triangle. Sorry, that should have been in, did we say PKT? Sorry, that's PKT, not RKT. Right, so it's PKT. So that's PKT. So T1 and T2 are equal to X, which is also equal to P1, okay? And we said these are base angles of an isosceles triangle. Base angles of isosceles triangle. Okay, right. Isosceles triangle PKT, right, which is the one that we spoke about there. Right, now, in this case, ladies and gents, what we simply know is that now if P1 is equal to X, and in this case, again, P1 plus 2, okay, so P1 plus 2, in fact, that's a much easier route. P1 plus 2 is equal to 90 degrees, right? So that's angles at semicircle. So angle at semicircle, okay, right? So P1 plus P2 is equal to 90, right? Now, think about it. If P1 plus P2 is equal to 90 and P1 is equal to X, what happens to P2? So P2, remember we said P1 plus P2. Okay, I'm trying to just write that. P1 plus P2 is equal to 90 degrees. We've just said that now. But we already know that P1 is equal to X. Did we actually? Yes, we did show that. So P1 is equal to X. So that's plus P2, which is equal to 90. So therefore, it means that P2 should be equal to 90 minus X. Okay, so note, we've got S being 90 minus X, right? We've got P2, which is 90 minus X. So we can then conclude that it means that P2 should therefore be equal to angle S. Why? Because both of them are 90 minus X. Okay, right. It's much easier for me when I work with that X. Okay, it's much easier to reference the angles in that regard. Okay, right. All right, let's move on to the next one. And if you don't mind, I'm just going to create some space here so that I'm able to just work as closely as possible to the diagram. You know, it's much easier when you refer to the diagram as you're working, right? So I hope that you've been able to see this one. So if you have not, you can always just, go back into the video and just watch that, right? Now let's go on to, they say, let's prove that triangle SPK, right? So I'm going to try and just highlight. So SPK, which is that big triangle over there, okay, right? We must prove that it is similar to PRK. So PRK is the smaller triangle within, right? So I'm going to highlight that in that red there. Right, I know it looks a little bit clumsy, okay? I'll try to remove there as much as I possibly can, right, so that we can see what we're doing. Okay, so we want to prove those two angles triangles rather, similar, right? So in this case, what I'm going to do is I'm going to try and prove that similarity using angles, right? So first of all, in both triangles, okay, let's keep in mind we're trying to prove SPK, triangle SPK, okay, similar to triangle PRK, okay, so we need to keep that in mind, right? In fact, let me just write it at the top there, SPK, okay, similar to triangle PRK. All right, now let's try and go for that. So in this case, what do we have, right? We know that K is common between the two. So in this case, we know that K2 is common. So K2 is common between the two triangles, isn't it? Okay, so in this case, right, you can say K2 is equal to K2, same difference, right? But we've also just proven, ladies and gents, that P2, which is inside that triangle PRK, right, is equal to angle S, right? We've just proven that. So angle S is equal to angle P2, okay? Right, we've just proven it. So we can say this has been proven, okay? Right, now think about it, ladies and gents. What does that leave in this case? It leaves angle R2 and R3, right, inside PRK, therefore equal to P2 and P3 in the bigger triangle, right? And we can just simply say that's the third angle of a triangle, right? So we're going to say, therefore, it means that R2 plus 3, right, would therefore be equal to P2 plus 3 in this case, right? Why? This is the third angle of a triangle, okay? Or you can say sum of angles on a triangle, right? So it holds, if the two angles are equal, then automatically it makes the third one to be equal, because then the sum of angles of a triangle are both equal to 180. So therefore it means that triangle SPK is similar to triangle PRK. And why is that? We say angle, angle, angle. Okay, right. So we've proven three angles equal, and so therefore we've proven similarity. Okay, right. Let's go on to the final question. Right, now they say to us, if it is further given that SR is equal to RK. All right, so what I'm going to do, ladies and gents, if you don't mind, because it does get a little bit confusing when we've got all of those things there, right? So they say if it is further given that SK, or rather SR is equal to RK, so SR is equal to RK. So I'm going to leave those there. Right, is equal to RK. And now they say prove that ST is equal to 6RK. Now let's see ST, right? So ST is that entire side, okay? So we need to relate ST to this side RK here. Right, now I'm going to remove this over here, okay, because what I do want to do is to work as closely as possible to the diagram. All right, now ladies and gents, let's first do this. Let's relate ST. Now remember, we said this is a 90-degree triangle, right? So you remember that K1 and K2 are 90 degrees. So we can say ST, so let's make ST squared, which would be equal to, that would be TK squared, okay? So that's TK squared plus, in this case, SK squared, okay? So we already have TK squared, all right, and SK squared there, right? So now that we're looking for SK, how can I relate SK to RK? Remember that SR is equal to RK. So we can actually say that ST squared is equal to, we'll come back to TK in just a bit, right? So that's TK squared plus. Now, instead of saying SK, I can say that's 2RK. Remember that because SK is equal to SR, in fact, let me write it out. So this is SR plus RK, right, squared. But remember, because SR is equal to RK, right, so I can substitute RK in the place of SR there. So that means that st squared is equal to, why did I remove that? Okay, because I want you to remember that they are equal. Because SR is equal to RK, right? This is given. Okay, so we know that st squared would be equal to tk squared, okay, plus, now remember, we said SR is equal to RK, so we can say RK plus RK, which is 2RK, so this is plus 2RK, but remember now, this is squared, okay, right. Now, this is looking a little bit hopeful because I want to have ST on the one side and RK on the other side, okay, right, so now I'm going to leave this this way. Okay, let's call it equation 1. Right, now where else can I relate TK? Right, and I want you to always remember, ladies and gents, there's a reason why they ask you to prove congruency. Okay, right? So I'm going to go to my, to that, what we've proved, the congruency that we've proven there, right? So that we can try and relate somewhat how SK relates there, right? Especially TK. So in my congruency, I know that because we said triangle SPK is similar, I keep saying congruency, but it's similarity, right? To PRK, right? So then it means SP over PR, right? SP over PR is equal to PK over RK, PK over RK, right? Which is equal to SK, okay, SK over PK, right? Over PK, right? So we said SP, right? So that's SP over PR, right? Now, in this case, I can see that, remember, what we're trying to drive towards is getting TK, right? An expression for TK. So in this case, I want you to note, I've got this guy over here, and that's because I'm seeing SK and RK there, right? So I've got PK squared. I'm going to cross multiply there. So PK squared, right? PK times PK will be equal to RK times SK, right? So in this case, I think we are almost there, right? So we've got PK squared is equal to RK times SK. But I want you to keep in mind, right? If you look at, if you look at PK, right? We had said that PK is actually equal to TK squared. Is actually equal to TK, right? So if you think about it, so we said PK is actually equal to TK, right? So in this case, I want you to please follow me in this, ladies and gents, right? So we've got equation 1. Let's call this equation 2, right? So we are saying PK is equal to RK, is equal to TK, right? TK, this was given to us, okay? Now, if they are equal, then we can substitute PK in the place of TK. So then it means that we've got ST squared, right? So we are substituting equation 2 into equation 1. So it means ST squared is equal to, instead of TK squared, I am going to put PK squared there. So this is equal to PK squared, right? plus, we said plus 2rk all squared. All right. Now, ladies and gents, I'm just going to make some space there. Okay, yeah, let's do this. So this is plus sk, plus rk squared, right? But what do we know about pk, right? We said pk is equal to rk multiplied by sk. So we're substituting equation 2 there. So st squared is equal to pk squared, but we know that pk is rk multiplied by sk. Okay, right? Remember, we've got this squared there, plus, right? So we've substituted that, plus 2rk all squared. Okay, we're almost there, ladies and gents. Just hang in there, hang in there. So st squared is equal to, now if you look at rk and sk again, right? We said rk, right? And sk, in fact, sk is that entire side there. So sk is 2 times rk. You remember that, right? So we said sk is 2 times rk. So that means this is going to be rk, right, times 2 times rk, right? All squared plus 2 times rk all squared, right? I'm sure you can see that we are almost there, ladies and gents, right? So what does this give us? Okay, so we are going to have, in this case, rk times 2rk, right? And please remember where we got that. Okay, so we're going to have 4rk squared. Yeah, I made an error somewhere there. This is going to be 4rk squared, right? So this, okay, and I see I actually substituted there. I said 2, okay? So this should be actually 2 pk squared, okay, rk squared. So that should be 2rk squared. So this would be plus 2rk squared. Okay, so in this case, what does this mean? All right, so we're going to now add those two. So this is going to be 6 times rk squared. Okay, and in this case, that simply means that st squared is equal to 6 rk squared. And so st would be equal to, if we take the square root on both sides, it should be equal to square root of 6 multiplied by rk. All right, and I want you to please note, I just made a slight error there, right? In this case, I think when I substituted 1, I squared the entire thing instead of just squaring the 2rk, right? But in this case, this is how we get to st being equal to square root of 6 rk. Right, please follow it. Try to do it on your own. So we used that proportionality, and you prove using the sides that are equal. We use, in fact, I forgot to even mention there, right? This is the proportionality theorem, right? That if angles are similar, or rather triangles are similar, then it means that their sides are also proportional. Okay, right. I hope that made sense, ladies and gents. Yeah, just I ask a little bit of pardon for where I made an error there, but I know one of them should have been actually 2rk squared. All right, I hope that made sense, ladies and gents, and that you enjoyed this question. Otherwise, I'll see you next time. Shap shap.